is this similar to what we did yesterday, and how is it different? Yeah, it's substitution, first of all, right? We did substitution yesterday, didn't we? How is it different? Right, exactly. How were the problems set up yesterday? Both of them, both of the equations in the system were y equals yesterday, weren't they? Okay, so that's how this is different. Okay, we need to practice some of these. Let's do number 1 together. We're going to talk about a couple more of these, and then we'll get going. Okay, of these 4 variables, which one do you think it would be the best to solve for? Number 1, it's your opinion. Okay, but there are better variables to solve for than others in some situations. Does that make sense? Okay, so in this particular problem, what do you think is the best variable to solve for? Which one? There's 2, babe. Pointing. You think it's best to solve for this y? This y? Okay, I will tell you, if I was doing this problem, I would solve for this y, just like you just said. Okay, because even though these are both by themselves, we could solve for this, but that would give us fractions, wouldn't it? Okay, so remember how I told you it's an opinion which one to solve for, but there's a better one? I don't want to deal with fractions unless I have to, right? Okay, and if I solve for either one of these, that's automatically going to give me a fraction, right? Can we get out of using fractions sometimes? No, right? Sometimes we have to have a fraction, but if we can start with a not fraction, that might be the best for us, yes? So if we're solving for this y, what do I want to do first? Okay, so if I subtract 2x from both sides, I get y equals 11 minus 2x. Yes? Well, what am I going to do with that 11 minus 2x? In the other equation, right? Exactly right. So now I have x times 11 minus 2x equals 14. Now what do I need to do? Distribute, very good. Excellent math vocabulary. 11x minus 2x squared equals 14. What kind of problem has this just become? Quadratic for sure. So what do I want it to equal? 0. So you can argue with me later on if you want to, but I'm going to move everything over to the right-hand side. You know me well enough to know by now like why I moved everything to the right-hand side, don't you? Why? Yeah, positive x squared term, right? Okay, so 2x squared minus 11x plus 14. I could have moved the 14 over there, but then I'd have to divide everything by -1 if I wanted a positive x squared term, right? So I might as well just move everything over there. It's not wrong the other way, though. Okay? Okay, so it's a trinomial. We talked a little bit yesterday about the best way to solve quadratics. Because there's an x term, we can't solve it with square roots, right? It's asking us to use substitutions. We can't graph it. Completing the square is almost never our first choice. So that leaves us 2 options, right? What are they? Factoring and quadratic formula. Okay? So first we want to try to factor, don't we? Factor is almost always quicker than quadratic formula. Almost always, just like I said. Okay? So factoring means AC is 2 times 14 was so 28. And then B is -11. So can you think of 2 numbers that multiply to be 28 and add to be -11? -4, -7, you okay with that? So I'm going to rewrite this problem with those 2 x values. Oops, that should be negative. Pretend that's a negative. So 2x squared minus 4x minus 7x plus 14. And then I factor by grouping, don't I? There's 4 terms. What's common in the first 2 terms? 2 x, right? So what's left if I take out a 2x? X minus 2. And what's common in the second two terms? Right, a 7, but remember what our parentheses has to look like? It has to look exactly like this one, right? So what I actually need to take out is a -7. Excellent. So that gives me an x minus 2. So what's common in these two? X minus 2. And what's left? Zero product property says what? Each of them, right? So x minus 2 equals 0, and 2x minus 7 equals 0. So I'm adding 2. Here I'm adding 7, and then dividing by 2, right? So here I get x equals 2, and here I get 7 over 2. Yes? Okay. So I'm going to, what did I just figure out? What my x's is. What my x's is? That's not what I meant to say, sorry. What my x's are. And I got 2 x's. So what does that mean? Oh, I have 2 solutions, right? So one of them starts 2 comma something, and another starts 7/2 comma something, right? And how do I figure out that something? Probably back here, right? Wouldn't this be the best place? I mean, I could go back to the beginning, but y is already solved for right here, right? So what is 2 times 2? So I have 11 minus 4. Does anybody know what 11 minus 4 is? So when x is 2, y is 7. Well, now I have 11 minus 2 times 7/2. Well, what's 7/2 times 2? Oh, yeah, that's just 7, right? So it's 11 minus 7. 4. Now, there's this really cool new thing. I don't think you guys have heard of it. When you find your answer, then you circle it. Yeah, I only say that because on your last couple tests, it's been really hard to find your answer sometimes. So let's circle our answers. Yeah, that was just a little joke. It's okay. Okay. Now, let's talk real quick about some of the rest of these problems. Okay, especially number 4. Comes into play a little bit on 3, a little bit on 5, but especially 4. Okay? Which variable are you going to try to solve for on 4? So, in my opinion, my personal opinion, I would definitely try to solve for y. And I would solve for this y. Because if I divide everything by 2, everything's already divisible by 2, so that's not going to give me any fractions, right? Here I'd have to divide everything by 3, and while that's fine and that's fine, that's going to give me a fraction, isn't it? Okay? But what I guess the bigger point I'm trying to make is, could you solve these for x? Not without a lot of work, because there's not just an x, there's an x squared. And somehow I'd have to get those combined together. And that, like I said, that's going to be like a lot, right? A lot of work. So let's keep ourselves choosing the best route, the most direct route, and let's try to solve for a y if there's an x squared and an x. Does that make sense? Okay? Like here it doesn't matter because I'll just square root both sides, right? Here, probably easier to solve for one of these two, yes? Okay? On number 5, which one would be easier to solve for? Probably one of these two, right? Because I could try to solve for one of the variables here, but I also have these 2 y's that I have to get together, or these 2 x's I have to get together. I might as well just solve for one of these already over here. Yes? Any questions about that? Then let's talk about some systems of nonlinear inequalities. Okay? How is a system of equations different from a system of inequalities? What do you have to do on inequalities that you don't have to do on equations? Yeah, we have to shade, right? Okay, so here's what we're going to do. On all of these, we're going to use these tables to help us plot these points, because, you know, yesterday we just kind of sketched. It was just kind of a general sketch that we want. When we're doing inequalities, we need way more exact. Okay, we need way more exact than that. So let's start with this first equation, right? Well, notice up here it's an inequality, right? But notice here it's an equation because right here the table is helping us get the boundary line. And then the inequality tells us where to shade, right? So do you see the difference in that? So let's use this equation to fill in this table, right? So we already said -4, if you put in x, -4 for x, you get a 6. What if you put in a -3, you get a 0? What if you put in a -2? What's -2 squared? 4, and what's 4 minus 2? 2, and 2 minus 6? -4, okay? What if we put in -1 squared? What's -1 squared? 1 minus 1, 0 minus 6, -6. What about 0? What's 0 squared? Plus 0, minus 6, okay, -6. And then 1 squared, 1 plus 1, 2 minus 6, -4. And then 2 squared, 4 plus 2, minus 6, 0. Now, one of the qualities we know about a quadratic, about a parabola, is that it's symmetric, right? Do you see the symmetry in this table? Starts here, right, and goes out and out. So what do you know about the vertex then? Does the vertex have an integer as an x value? It doesn't, right? It's a fraction. It's somewhere between -1 and 0, and in fact, exactly in between -1 and 0, right? Okay, so let's go ahead and plot these points. -4, 6. -3, 0. -2, -4. -1, -6. 0, -6. 1, -4, and 2, 0. Okay, so far? Is there another point over here that I know exists, but it's not on my table because my table didn't go that far? Where is it? Three, 6? How do you know that there's a point 3, 6? Oh yeah, it's symmetric, isn't it? So I know there's a point right there. Okay, now I need to go back up to, before I do anything else, I need to go back up to my inequality and I need to decide, what do I need to decide? If it's solid or dotted, right? That's what I need to decide first. Is this solid or dotted? Solid because why? Or equal to, right? Okay, so I'm going to go ahead and draw this in. And now I need to decide where to shade. Remember with parabolas, we either shade inside or we shade outside, right? So with parabolas, we choose a point. Which one's the easiest point to choose? 0, 0. 0 is greater than 0 plus 0 minus 6. 0 is greater than -6. Is that a true statement or a false statement? Is 0 greater than or equal to -6? It's either true or false. It is true, right? 0 is greater than or equal to -6. So I'm going to shade toward the true area. So for this particular parabola, I'm shading inside of the parabola. Does that make sense? Now let's go to the other inequality. What kind of shape is this? It's a line, right? So it's just x plus 3. So let's go ahead and fill in our table. They've already done the first two for us, but we can always check it, right? -3 plus 3, -2 plus 3. Okay, so that's good, right? -1 plus 3, 0 plus 3, 1 plus 3, 2 plus 3, and 3 plus 3. Okay, so let's go ahead and plot those points as well on the same graph, remember. -3, 0, -2, 1, -1, 2, 0, 3, 1, 4, 6. Are there some, where'd you get that? Are there some other points on this line that I can't, that are not on the table, but I also know exist? So like right here and right here. And then right here and here and here and here and here. Now, are those required for our line? No, but it sure makes it a lot easier to see the whole line, doesn't it? Okay, so let's go back over to the inequality from the beginning. And what are we thinking about? Solid or dotted, so you say solid because it's or equal to, right? So I can draw it in. Now I have to decide where to shade. And am I going to shade above or below? How do you know? It's less than, so we shade below. So now that we're done with both, in this case both, there could be more than two, right? But in this case we're done with both inequalities. We've got the table, we've plotted the points, we've graphed them, we shaded them. Now we shade for the problem, right? Where am I going to end up shading for this problem, for this system? So below the line, but inside the parabola, right? So there. Now remember, please don't get too OCD on me here. You just need to shade the area so I know where to shade. We don't have to get every single little tiny little speck. Not saying there's anything wrong with OCD. I just need you to fight it a little bit when we're talking about this. Yes? Okay. Last thing to do, list some possible points. How many points are there in this shaded area? In fact, infinite, right? There's an infinite number of points in there. Okay. Let me hear from this front table right here. You guys, tell me one possible point. 1, 1. Let's see. 1, 1. Is that in the shaded area? Yes. Okay. What about back table right here? Give me another point. -2, 1. So let's see. -2. Ooh, that's a tricky one. Is -2, 1 part of the solution? Because it's on the solid line. Because it's on the solid line, it is part of the solution. If this said just less than, would that be part of the solution? No, it would not. If it's on a dotted line, it's not part of the solution. If it's on a solid line, it absolutely is part of the solution. Okay? What about you guys? Tell me one. 1, 0. Is that part of the solution? 1, 0. Yeah. What about from you guys? -1, -4. Is that what you said? -1, 1, 2, 3. Is that part of the solution? Yes. All right. One table left. 2, 2. Is that part of the solution? Now I get a choice. What about this point? Don't say no. That's rude. What about this point? Why didn't any of you guys pick points like that? You naturally go to the integers, don't you? Okay. What I'm trying to get you to think about is it's not just all of these intersections in here that are solutions, are they? -0.08, which is really, really close to the line, and then -1. So like right here-ish, isn't that part of the solution? It is, right? That's how there are infinitely many points in this shaded area, because of all the points like this. You know, I'm just being silly, but also serious at the same time, right? It's not just the integers we have to think about, but the crazy ones as well. Yes? Any questions about solving a system of nonlinear inequalities? So go through, do the steps that we just did, fill in the table, decide if it's solid or dotted. fill in the table, plot them, decide if it's solid or dotted, then you do shading, yes? And then decide points that lie in the shaded region. Let's go. We were just going around the room, make sure we have all the options, right? That everybody had a chance. But let's make sure to get 5. Yes? In all the ones that you have to do on the rest of this page, make sure you get 5 points in the shaded region, okay? So you have 2, 3, and 4 on this worksheet to do, and you have 2, 3, 4, 5, 6 on this worksheet to do, yes? Any questions?